My name's Tim Griffin. I'm going to talk about some work that I've been doing at Bell Labs with Bruce Shepard and Gordon Wilfong.
Now, turn off the light for a second. Let's just put it up here.
I know. Sounds good. Okay. And I know this board has seen a lot of talks on BGP and on various aspects. I think this is probably the first talk on the metaphysics of BGP. Okay.
I think it's your lanyard that's interfering.
This?
Yeah. Why don't you take it off?
How's that?
I don't know. Start talking.
Okay. Here we go. Okay, so I want to ask, what problem is BGP solving? And of course, it's solving the interdomain routing problem, but here's the way I mean it. And here, well, maybe I should tell you why I started thinking about this problem, because I was writing some code on top of the RA tool set, and what I wanted to do was pull in RPSL policies from databases and then do some analysis, sort of end-to-end consistency analysis, or check for certain kinds of routing anomalies. And I was having a hard time because I didn't really have semantics for BGP. You know what I mean? I wanted to first of all simplify things along one dimension. I just wanted to get rid of that whole notion of dynamics of BGP. So I could just think of a collection of routing policies as some system of constraints that I wanted to solve. Okay, and then I wanted to simplify it along another dimension, so they sort of get rid of all of that complexity of the interaction of policies along a path, of things like that. So, and I wanted to use this in designing algorithms for heuristics, really, for analysis of RPSL policies. Okay, and it turned out that we came up with a simple model, and it was also useful for other kinds of analysis of BGP that I'll talk about toward the end, and also is useful in the design of some extensions and analysis of proposals for BGP. But I'm not really going to talk about some of that stuff today because it's kind of researchy. What I hope to talk about is, what I hope you get out of this talk is some sort of fun way of looking at BGP, and also some framework that makes it a little easier to discuss certain kinds of routing anomalies that can happen with BGP. Okay? So what I want to do is, we all know that there's this shortest path problem out there. It's very simple. You can describe it to anyone, so any math geek, for example, will understand this problem. They don't have to know anything about networking. It's a very simple problem. You have a graph, some weights. You want to find shortest paths in that. Okay? And so that problem underlies these well-known protocols, RIP, OSPF, and ISIS. And those things are fairly complicated distributed algorithms for solving the shortest path problem. Okay? So I want to find an X, so a problem, that is to BGP as the shortest path problem is to these IGPs. Okay? And I want it to be as simple as possible. Okay? So, for example, I want it to fit on 2 slides. Okay, so here's the problem that we came up with. Here's the way of stating it. We call it the stable paths problem. And again, forget about all of the complexities, let's say, of BGP and the dynamics. I'm just going to give you a very simple graph problem. And the problem is, you have a graph with labeled nodes, and there's a special node labeled 0. And everyone else, all the other nodes, have collections of paths to that node 0, and it's every node has some subset of all possible paths from that node to the 0 node, and these are called the permitted paths at that node. So, for example, node 3 in this diagram has just one path. 30, and node 2 has 2 paths to the origin. Okay? And each one has a ranking on those paths. So, and I've listed it so that they rank, the highest ranked path is on the top of the list. So for example, node 2 likes the path 210 more than it likes the path 20. Okay? Now, that's it. And so, you know, intuitively, the idea here is that 0 is some, let's say, some AS announcing an address block. And what we're looking at is sort of the distilled policies, how everyone wants to get to that address block. Okay? So I'm only looking at one address block at a time here. And I'm not going to get into the translation from, let's say, a set of RPSL policies to an instance of the stable path problem, because it gets really messy, especially when you're dealing with IBGP, for example. So intuitively, we can think of, just as a first cut, that each node here represents an AS. Okay? And it's a little bit simpler thinking about it that way, because these paths represent AS paths. Fine, but in general, when you deal with IBGP, you're actually dealing, the paths actually are paths between routers, and these nodes represent routers, okay? But I'm not going to get into the messiness of the translation. Okay, everybody understand what an instance of the problem is? Okay. Now I want to tell you what a solution is. Okay, so a solution, how do I solve a stable paths problem? What I do is I come up with an assignment of paths to nodes, okay? So the two things are true. Don't try to read that stuff. I'll just tell you what it means. One thing is it's a consistent assignment, and that is it's a tree. You know, the assignment of paths induces a tree rooted at 0, okay? And the other thing is that it's stable. Every path, every node is stable in the following sense, is that it has, of all the paths going through its neighbors that are consistent with their assignment, it has the highest ranked path possible. Okay? So let's look at this. The underlined, the red paths here represent a solution to this particular stable path problem. And for example, 2 is not terribly happy. It has this path that it doesn't like as much as 210, but it can't have 210 because that's not consistent with what is assigned at 1. Okay. 4, for example, couldn't be assigned 430 because of a stability condition, because it can adopt the path given the assignment that's at 2. It can adopt the path 420, which is better than 430, so it's going to take that path. Okay. So it has to have that path in a stable assignment, given what is assigned at 2 in this case. Okay? So is that clear? And also we can have a node like 5 here that doesn't get anything. So in general, the stable path problem is not a spanning tree, and it's also not a shortest path tree in general. Okay? So let's just look at another example real quick. Just first of all, this illustrates that there can be multiple solutions to a stable path problem. Here I have a problem where 1 prefers to go through 2 and 2 prefers to go through 1. I call it disagree because there are 2 solutions here illustrated, and somebody always loses. Somebody always has to take the path they prefer less. Okay? And in this case, just to illustrate what stability is, if you assigned 10 and 20, the direct path to each node, well then that's not a stable assignment because each of those nodes can do better by going through its neighbor. Okay? So I want to illustrate in the next, these things aren't directly, if you look at this, it sort of looks like, 1 and 2 are maybe doing something strange, right? And that could be the case. But let's look at how RPSL might map down to this. I'm going to show you 3 sets of RPSL policies that the actual BGP policies that map down to the same stable paths problem. They all map down to that problem, disagree. And the first one is sort of a direct encoding of what you see at those nodes, is that is 1 just prefers anything it sees announced from 2. So it sets a higher local preference. which happens to be in RPSL a lower pref. Okay, it's just sort of a direct encoding. I'm just going to use local preference to do that. Another encoding is very different. One says, okay, if you send me a certain community value, I'll prefer it more. And that's community 1, And 2 says, well, if you send me community 2, I'll prefer the route more. And what's strange here is that the 0, the origin, is sending out announcements, and it's sending up to, when it sends an announcement up to 1, it's attaching the community for 2's preference. And when it sends up the announcement to 2, it attaches the community for 1's preference. And so that ends up inducing those preferences that you see in the stable path problem at 1 and 2, but it's not really there. It's not 1 and 2's policy exactly. It's the interaction of the announcements from 1 and the sort of generic policies at 1 and 2. Okay? And finally, it was sort of a combination. 0 pads out on the 0-1 link so that 1 likes things coming from 2, and 2 has local preference set so that it prefers things from 1. Okay? Now, you could sort of get a sense here why this kind of model helped in writing some code to do static analysis of policies, because you can sort of boil down all of that complexity of interaction down to kind of a very simple canonical form, and then do some analysis there. Okay? So that's what's going on here. Okay, so let's look at how just this fact that there can be multiple solutions to a stable path problem, how that can explain or model a sort of very common routing anomaly. And I'm calling it route triggering here. I'm not sure if that's a well-known term. I got it from Alex Rudnev, but it basically means you have a primary link and a backup link, and you don't want any traffic going over your backup link. Fine, and so your primary goes down, all the traffic switches to the backup link, and then what happens is your primary comes back up, and you still got traffic on your backup link. What happened? Okay, so here's a really simplistic model where we're looking at, you look at node 0 there, and all the traffic is coming in on the primary link, and then that link goes down, and we have another solution to a simpler problem. And now you can imagine the link comes up, but hey, there's nothing to prevent it from adopting a different solution to the stable path problem. Okay? And there we see that both 3 and 1 have routes directly to 0. Okay? Now, I've sort of, I've gone this far without really talking about dynamic semantics at all. Okay? So we can sort of imagine a simple protocol for this stable path problem where every node is just listening to announcements from its neighbors about what path they have, and then making their decisions based on what the best possible path is, right? So it's very simplified version of BGP. Okay? So if we think about that protocol, well, what happens if there's no solution to the stable path problem? Turns out, define a stable path problem has no solution. Okay? So remember what I mean by solution. It's everybody's happy. Not necessarily happy, they're content. They can't get any better given what their neighbors have. So if there's no solution, and if every node, all they see is their neighbors, well, then somebody's always going to think they can get better. Somebody's always going to be changing their path, and that the protocol can't converge, right? If it converged, we'd have a solution, but there's no solution. So it turns out that this is sort of a simple model of how BGP can diverge. And this is this observation was made in '96. How many people are familiar with this possibility? The basic idea is that there's no guarantee that the BGP routing policies of a collection of autonomous systems is consistent in any sense, that there is a solution, that there is some static routing, right? So BGP can actually diverge, just exchange routing messages forever. Okay? So the bottom picture is just sort of the stable path problem way of looking at that, and it just says, yeah, if there's no solution at all, well, you have to diverge. But it turns out there's cases where there is a solution and you can diverge also, and I'll give an example of that. Okay. Okay. So here's a system that has no solution. It's called Bad Gadget. And basically, the idea is that everybody prefers a one or two hop, a two-hop counterclockwise path to the origin. Okay, and it's fairly simple to see that there's no stable assignment. For example, if 1 took that direct path in to 0, well then, because if we're assuming the assignment is stable, that implies that 2 has to take 2, 1, 0. Okay. And that implies that, well, 4 can't take 4, 2, 0, so that implies that 3 is taking 3, 0. But if 3 is taking 3, 0, well, if it's a stable assignment, then 1 can't be taking 1, 0. It has to be taking 1, 3, 0, because that's the best it can do given the assignment at 3. A contradiction. So you can go through case analysis like this. There's no solution. So if we think about those 3 different sets of RPSL policies that map down to that simple system disagree, we can come up with a dozen policies at the BGP level that could map down to this system. And whether or not they're all sensible in any way, I'm not sure, but then there's always the possibility of misconfiguration, right? But there you go. So one way of interpreting that observation that Varadin et al. Made is that well, this problem that's being solved doesn't necessarily have to have a solution. Now let's take this problem here and add a link between 0 and 4, and let's make 4 prefer that most. So that's this system called surprise, and it has a solution. The underlined, the red assignments is a unique solution to this problem. So 4 takes the direct path. Great, and everybody else locks in on another route. The problem with this is that you can have a stable routing, right? And boom, when that 0-4 link goes down, it becomes Bad Gadget. Okay, so what this example illustrates is that everything can be great, but lurking in your never-tested backup policies is a problem that you're not going to see until some link goes down. Okay? Another problem, and this is, I kind of like this slide. It just looks nice. This is an example where there is a solution, but you can also diverge. Okay, and so on the right-hand side is that disagree subsystem, right? Remember, it has 2 distinct solutions. And we have over here on the left-hand side something that, well, if 1 picks the direct path, to 0, then everything's okay. Everybody sort of locks into 3 and takes that path. However, if 1 locks into the 1, 2, 0 path, then boom, the left-hand side becomes a Bad Gadget, and there's nothing you can do. It will never never converge after that point. Okay? So now notice that in these Bad Gadget kind of examples, there's always several autonomous systems that are preferring some longer path over a shorter path, right? Actually, it turns out that that's always going to be the case. So you would like to say that if I configure, let's say all routers in the world are configured so that they don't use local pref. Okay, so in other words, basically the decision process is pick shortest AS paths and then do some tie breaking. And you'd like to use that as sort of a baseline for analyzing, let's say, proposed extensions or whatever to BGP, because you say, well, let's start from that safe world and see if we can get into trouble by adding some new feature or whatever. So here's an example. So the idea here is, suppose you're in a world where there's no local pref, but we do have confederations. Can we get into trouble if within a confederation you take, when you're measuring AS path length, you take member ASs into account? Okay, it seems like you could code that up yourself if you wanted to, or your vendor could provide a knob for doing that kind of thing. And here's just a simple example where you get a bad gadget out of that. So the big blue circles are confederations, and they each have 2 member ASs. And so for example, Q, the router Q, has 3 paths to 0. They're all of length 2 from the perspective of its BGP table, let's say. And so it just breaks ties using maybe the IP address of Z and R and A. Okay, and so it broke ties preferring to go through 3. And now everybody does the same kind of thing. They just break ties going to the left, and boom, you've got a problem. Okay. Here's another example. This is just, again, suppose we're living in the world where there is no local preference, but there is, so we know that world's safe. Now let's add the prefer me global community. Okay, so here's an example where in the gray boxes are sort of the BGP level policies. Everybody's doing sane things. There's nothing weird about it. And paths are being, equal length paths, for example, at 1 and 3 are just being, there's tie breaking going on there, so they just happen to pick this counterclockwise path. And then 5 here is announcing prefer me up to 2. And so what we're seeing in 2's policies in the so it's in the BGP world, it's just saying, hey, I'm doing shortest paths, basically. But in the SPP world, we see that this one path is preferred over the other, and then you get this bad gadget. Now, this isn't saying that prefer me is bad, or it's not saying it's good, or anything like that. It's just saying it's very powerful. Okay? It's just saying in a world where everything is okay, only one use of this attribute is enough to get you into a situation where you won't converge. Okay? So perhaps there are some guidelines that need to be followed when using these kind of things, or use them carefully, something like that. Okay. So what's to be done here about this particular problem? Well, one approach, of course, is to put the problem really was originally looking at was, well, how do we pull out RPSL policies out of a database and check them for consistency? We want to say, hey, there's not going to be any problem here, or there is going to be a problem, potentially, if this link goes down, let's say. And we've done some analysis on that, and again, this is kind of researchy stuff, but it turns out to be really hard. Even if you had complete information of RPSL policies, it turns out to be an NP-complete problem to identify solvability and that kind of thing. So that doesn't mean that it's not worthwhile still to come up with some heuristics that work pretty well in practice, and I think that's definitely an area that we're going to do some work in. Okay. Another approach is to just recognize that this forum like this, recognize that there is a possibility of BGP divergence, and try to come up with, let's say, recommendations or policies and how to identify that and how to address that. One thing to do, I think it would be fun, would be to, with one prefix, let's say, to actually set up in the backbone between large tier 1 ISPs, set up an oscillation like this intentionally, so that we could use the kind of infrastructure Craig talked about to measure what it looks like. What does it look like when this kind of thing happens? And then maybe use that to come up with some recommendations or guidelines. Okay. Another approach is a dynamic approach, some sort of dynamic break on BGP oscillation. Now, route flap dampening doesn't solve the divergence problem. All it does is make it run in slow motion. Okay. So what will happen is, let's say in a bad gadget, is you'll just slow it down. It'll never stop. Okay. And we've done some experiments on that. But so one thing, and again, this is sort of a researchy topic. We've come up using that SPP formalism. We've come up with a proposal to actually extend the protocol with extra information, where you can dynamically detect a policy-based oscillation and recognize it as a policy-based oscillation. And you can see all of the AES, the autonomous systems that are involved in that, policy conflict, okay? So again, that's sort of at the level of this SPP, very low level. Now it's kind of it's a research problem right now to bring that up to the level of BGP, and is it scalable, is it robust, things like that. So some shameless plugs on some work we've done, and again, this is sort of in the academic community. We had a paper in SIGCOMM last year, showing that a static analysis essentially of RPSL is very hard. Okay. We also, in ICMP, we had a paper that sort of used this SPP model, came up with some sufficient conditions for safety, sanity, things like that. And then in InfoComm coming up next month, we used that model to develop this extension, this safe extension to a simplified BGP protocol. Okay. The SIGCOMM paper and the InfoComm paper are available online at the SIGCOMM and InfoComm sites. If you want the ICNP paper, send me mail. A recent paper that's going to appear in SIGmetrics by Li-Shin Gao and Jennifer Rexford sort of uses some of this formalism and shows that, well, if we make certain assumptions about the world and how routes are exchanged, then they can prove that everything's always going to be okay. Okay. And so the question is, are the assumptions valid, and how well do they model what's really going on, the complexity of routing policies really out there today? And of course, they assume that there isn't going to be any misconfiguration there. And if you're interested in that paper, I suggest sending mail to Jennifer at AT&T Labs. Okay.
Questions for Tim?
Maybe bring up the mic.
Sean Darlin. I'm interested in your opinion, using the current tools that the operators have available to them. Is there any intervention they can make that would stop this oscillation if they detected it by some other means?
Well, I think the big problem is when you see this kind of oscillation, from one path to another, you don't really know what the source is. You don't know if it's some flaky interface somewhere, or there's no way of telling right now by looking why this route is flapping. Okay, that's why I suggest that I know of. That's why I was suggesting that maybe some experiments be done so that we can get a feeling for what it actually looks like when it happens, right? So perhaps it looks a little different than the kind of flaky router flapping that we're used to seeing. Okay.
Yeah, maybe I just wasn't paying attention close enough, but it looks like all of these examples of problems depend on peers redistributing routes learned from other peers to each other, which is currently not the case in the vast majority of the large backbone routers. You tend to only originate the routes that you're receiving from customers to peers, not other peers.
Right.
So that eliminates a lot of those cases of problems.
Yeah, and I think that's essentially the idea of the Li-Shin Gao and Jennifer Rexford paper is that kind of model, right? But then
think
again,
that's what's already implemented.
right, but we don't, the thing is that these are this is kind of a worst case analysis, right? That as the complexity of BGP policy becomes, sort of unmanageable, and you look at the interaction of policies between peers, and also throw in things like misconfiguration, right? And the fact that link failure can activate policies that might not be so obvious at first, right? I think there's a reason to concern here. I'm not saying the sky is falling or anything like that. Obviously, I just think there's reason to be aware of the problem and to be somewhat concerned with it.
Well, I'm not saying that we shouldn't be concerned, and I'm not saying that these problems aren't real, but I think we need to be aware that the default configuration of providers and what people are recommending and requiring of their peers is a condition where these types of failures are not going to be epidemic. Now, obviously, I've seen plenty of misconfigurations where you'll end up with something very like what these problems describe happening with continuous route looping. And the only way to clear it is to pretty much shut down everything related to that path.
Right.
But the default configuration is that you're not redistributing routes, that you're not originating to other peers in a common exchange
Right.
for lots of very good reasons.
Okay.
If you, this is a sort of a related question about this presentation and a question sort of for Craig. If you're looking from the perspective of a number of different providers, and only some providers have these conflicting policies, then have you ever looked at it from the perspective of saying, well, we see these prefixes churning, but only in a few different ASs, not globally, and looking past the BGP dampening window. So maybe there isn't actually, the T1 going up and down causing it. Maybe it's some sort of oscillation. Or at least you have that data so you could run that kind of analysis sort of after the fact.
That would be a great thing to look for in all of that data that's being collected out there.
Right. Obviously, you lose if it's the ASs transiting someone that are, having this problem. But as was pointed out, normally those ASs aren't transiting each other also, although sometimes that happens.
Right.
I think all that makes a lot of sense. The difficulty up till now has been that there's been so much junk in the BGP streams that any type of rational analysis on trying to find patterns has been a bit nonsensical. But because we've gotten rid of some of these pathologies, I think, and things really are being deployed in new router, so hopefully in the future.